When most people think about physics, they split their thinking into two separate categories. The first one is what physicists would call classical physics, and this deals with things like throwing a ball or having two balls collide into each other. And it deals with things that we can observe with the naked eye, things like velocity, speed, position, things like that. The second type of physics that most people kind of completely disregard is what physicists refer to as quantum physics. And to the average person, quantum physics sounds like a sort of magic. It sounds like something that they don't think they should be able to understand, and they don't try to understand. I'm going to tell you that quantum physics actually isn't that complicated. And what I'm going to do in this video is attempt to explain it for you without being as boring as watching paint dry. Let's see if I can do that. The beginning of what we now refer to as quantum physics or quantum mechanics started with a man named Max Planck. Way back in 1901, which is basically caveman times, Max Planck came up with a solution to a problem that no physicist back then could solve, called the ultraviolet catastrophe or the black body radiation problem. A black body is an object that absorbs all radiation that comes to it. They're called black bodies because if something is to absorb all radiation, that would mean it absorbs all visible light. So if you looked at it, it would appear black. In actuality, black bodies are not actually black because they also emit radiation, which the human eye can pick up and perceive as color. But what no physicist could explain was this. Right now, I'm showing you a graph of what's known as a black body distribution, which you might have guessed is the distribution of radiation emitted by a black body. As you can see, the graph follows a sort of upside down parabola shape, where it is at its minimum at 0 and its maximum point. However, classical electromagnetism, or in layman's terms, normal physics that physicists accepted at the time, could not explain this. The theories that people believed back then showed that this would not be a parabola shape. Rather, it would be an exponential shape increasing forever. However, experiments showed this was clearly not the case. No one could explain this until Max Planck in 1901. Planck presented a theory that seemingly fit all the things that physicists couldn't explain. He theorized that energy from black bodies comes in discrete packets, and he called them quanta. The energy of each quanta was equal to hf, or rather the frequency multiplied by something called Planck's constant, something that, you guessed it, Planck calculated. Planck's constant had a value of 6.63 times 10 to the negative 34 joules per second. Planck's theory that energy was made up of single units, and that you could, in theory, have a single unit of energy that was the minimum value of energy that could exist in the universe, no one believed that. No one accepted this because it just seemed so preposterous. That didn't mean that it stopped people from using his findings, though. Eventually, people accepted his theory because it just fit so well into the experiments that were being performed. In particular, the equation that Planck came up with, E equals hf, was incredibly significant because it showed a couple of things. Firstly, it showed that there was indeed a minimum value of energy, and this was h. Secondly, it paved the way for future scientific discoveries because although Planck only applied the theory of quanta, which is minimum units of a value, to the idea of black body radiation, that idea would actually hold for many other concepts in the universe. This would be first showcased by a famous man whose name I'm sure you know, Albert Einstein. He actually came up with more things than E equals mc squared. This discovery was known as the photoelectric effect, and it was another explanation for a phenomenon that scientists, for the life of them, could not explain. The problem was that if you took light and shone it at a piece of metal, sometimes electrons would bounce off of the metal. The thing that nobody could explain for the life of them was that the amount of electrons that bounced off of the metal had nothing to do with the intensity of the light. Rather, it had to do with the frequency of the light, which meant that if you took a light with high frequency, but a very dim beam, there was a chance electrons would bounce off. But if you took a massive flashlight, a massive beam of light that had a low frequency, no electrons would bounce off of the metal. And this didn't fall in line with any explanation that scientists could come up with either. That is, until Einstein tried applying the concept of quantum to light. 4 years after Planck's discovery, in 1905, Einstein proposed that light was actually made up of particles called photons. And these photons were the minimum unit that light could have. This explained the photoelectric effect because if you view light as a collection of particles raining down from the flashlight, then if the photon carries enough energy to bounce off of the metal, or rather to displace an electron from the metal, that would mean it doesn't matter how intense the light is. Even if you had one photon, if it had a high enough frequency to have an electron bounce off the metal, it would be able to do that. However, inversely, if you have a giant beam of very weak photons, no matter how hard they tried, no individual photon could cause an electron to bounce off the metal, therefore explaining the photoelectric effect. Finally, scientists had to accept that some phenomenon in the universe had minimum units. For example, photons of light or quantum of blackbody radiation, because that was the only possible way to explain things that we saw in experiments. So, because of this, for a while people thought that light was a particle. This view was famously contested by an experiment known as the double slit experiment. The way the double slit experiment worked was like this. Suppose you had two different walls. Then you poke two holes into the first wall. If you believed that light was a particle and then proceeded to shine a light at the two holes in the first wall, you would expect one thing to happen. There would be two spots on the second wall, corresponding to the location of holes on the first wall. However, this is not what you see. What actually happens is multiple spots appear on the second wall, and their intensity varies. This can only be explained if light is actually a wave. Because if light was a wave, then we could picture the interference between the light coming from the two holes in the wall combining at certain points and destroying the lights at other points to have this sort of multiple dots pattern. So what happened next? Were physicists now convinced that light was a wave? Was light actually a particle, and was this experiment just a fluke that would be forever unexplainable? Or was there rather a separate explanation?
Objection! Hold it! Objection! Objection!
So there we have it, the solution. Is light a wave? Is the particle? It's both. What physicists next discussed was whether photons, which they had now established existed, had energy and momentum. The first person to design an experiment showcasing that photons had momentum went by the name of A.H. Compton, and this is the experiment he designed. What Compton did is shoot X-rays at a thin metal foil and then observe them. What he observed was that X-rays and electrons would bounce off of the metal foil and lose energy, thus showcasing that photons did, in fact, have momentum as well as energy. If we use the understanding of light as a particle, then we can apply classical physics equations to it. And one classical physics equation being applied to light would be the equation for momentum. So, due to previous findings, we can assume that the momentum of a photon is equal to the energy of the photon divided by c, or the speed of light. Einstein's quantum theory gave the equation that E, the energy of a photon, is equal to hf, Planck's constant multiplied by frequency. Further, the equation for the speed of a wave is given as v equals f lambda. Therefore, we can substitute that because we know that c is actually just the speed of light, or rather, c equals f lambda for light. Therefore, we now have the equation that the momentum of a photon is hf divided by f lambda. Cancel out f, and we now have the final equation that we can use to solve problems regarding Compton's experiment, which is the momentum of a photon is equal to h divided by lambda. While Compton was busy figuring out whether or not electrons had momentum, on the other side of the world, some French guy was trying to figure out if you could apply the same concept that light was both a particle and a wave to other things, in particular electrons. This is his name, and if by looking at it you assume that it was pronounced Louis de Broglie, you would be normal. You would also be incorrect. His name is pronounced Louis de Broglie.
Louis de Broglie.
Like that. So what Mr. French guy did is he simply took the equation that Compton had applied to light and said, hey, what if we took that and then rearranged it? So that now the equation is solving for the wavelength if we know the momentum of a particle, any particle, such as an electron. So how do you test a hypothesis like that? Well, the easiest way to test if something is a wave to check whether or not interference exists within that thing. So, the logical thing to do would be to design an experiment using electrons that showcased whether or not electrons had interference, or exhibited interference or not. And what do you know? You can do an experiment like that. This experiment we already talked about, with the double slit experiment. You can do that with electrons too. And it shows the exact same results. Electrons have interference. French guy was right. Before we move on to the next segment, let's do a quick recap. We talked about these equations in this segment. The energy of a photon is E equals hf, which means the energy of a photon equals Planck's constant times frequency. P equals h over lambda, which means the momentum of a photon is equal to Planck's constant divided by the wavelength of the light. The momentum of a photon can also be written as P equals E over c, or momentum is equal to the energy of the photon divided by the speed of light. And finally, the new equation that we just talked about, the French guy wavelength. Lambda equals h over p, which means that the wavelength of a particle, such as an electron, is equal to Planck's constant divided by the momentum of that particle. Recall that Planck's constant, h, is equal to 6.63 times 10 to the negative 34. Also remember that c is approximately equal to 3 times 10 to the power of 8. So let's try and use these equations to solve some problems. The final concept I'm going to be explaining in this video is known as the Heisenberg uncertainty principle. It's made its way into pop culture to the point where some people think that it's just another way of saying the expression, you can't have your cake and eat it too. This couldn't be further from the truth. Specifically, the Heisenberg uncertainty principle refers to limitations on measurements done on quantum systems. Simply put, Heisenberg states that you cannot measure an object's position and momentum at the same time. If your measurements of the object's position become more accurate, then the measurements for that object's momentum must become less accurate, and vice versa. The mathematical model that Heisenberg derived is that delta x times delta p is always greater or equal than h over 4 pi, which is to say that the uncertainty in the object's position multiplied by the uncertainty in the object's momentum always are greater or equal to Planck's constant divided by 4 pi. Finally, let's talk about why we, average people, should care about quantum physics. Many people have this misconception that quantum physics is something that only people with a PhD in physics actually care about. That's not true in the slightest. In fact, many of the greatest technological innovations that we've made in the past couple of decades or so happened due to our newfound understanding of quantum physics. I'm going to give 3 examples of technologies produced by quantum physics that help the average person. The first thing is electron microscopes. They work because of a French guy whose name I can't pronounce, wavelengths. How they operate is an electron microscope will shoot electrons at an object that is incredibly tiny. And what that does is allows for the electrons to bounce off of the object. Given that, that we can test for the electrons to bounce off the object, and given that we can use the object's velocity to solve for its momentum because of the fact that P equals mv, and we know the mass of an electron because it's a constant, then we can figure out the French guy wavelength of each electron. Knowing all of the wavelengths of the electron that have bounced off of the tiny object will allow us to create an image with a computer that is far more accurate than any light-based microscope can do. The average person should care about electron microscopes because they're actually incredibly important in many fields, such as the medical field, because they allow us to create an image of things that are incredibly tiny. We can allow doctors to create images of things such as cells, and this will help them better treat diseases that the average person could get, therefore advancing medical innovation. The second innovation that was brought forth because of quantum physics is also related to the medical field. Specifically, I'm talking about PET scans. How PET scans work is the patient undertaking a scan will consume a pill which releases positrons, which are basically antimatter electrons. And what this does is when a positron collides with an electron, it releases 2 photons. And these photons can be picked up because of what we understand based on quantum physics. This photon emission allows doctors to create a scan of the patient's inner workings due to the innovations that we know based on quantum physics. Finally, an innovation that you definitely care about if you're watching this video, quantum physics is allowing for innovation of better chip designs, specifically quantum computers. This is due to how chips store information. Current chips store information in binary, meaning that bits can be 1 or 0. However, a quantum physics phenomenon that expands on what we learned in today's video, called quantum superposition, allows for a bit to have 0, 1, or both at the same time. By applying this quantum physics concept to computer chips, scientists are able to create chips that, although are the exact same size, can store much more information. This will allow us to solve new mathematical problems, develop more accurate models, and have faster computers overall. This is something that we should definitely look forward to in the near future. Alright, thanks for watching today's video. To recap, we went over a brief history of quantum physics as a whole. Starting off with how Max Planck solved the black-body radiation problem, then moving on to how Einstein solved the photoelectric problem. After that, we discussed properties of light, such as how it's made up of individual packets called photons, and how photons have momentum and energy. We applied this same thinking to electron and found that electrons also have wavelengths, which was discovered by a French guy whose name I can't pronounce. After doing a recap by solving some problems, we looked at some applications of these physics concepts in the modern world. That's all for today. Thank you so much for watching, and I'll see you next time.